So we go on to the next presentation, Tor-Martin Tveit. Tor-Martin is responsible for the heat pump technology in Olvondo as a CTO, and he has full responsibility for the R&D projects and also for the roadmaps of integration this Stirling heat pump technology into industrial processes. Tor-Martin has also some teaching or academic responsibility because he is an associate professor at the Abo Academy University in Finland. So I hope you can also share your knowledge of heat pumps and steam heat pumps in the university. So you have more than 15 years of experience. So let us see what you can present us today on Olvondo technology. So Tor-Martin, please start with your presentation.
Yes, thank you. So yes, I'm going to talk about the Stirling cycle applied to the steam generating heat pumps. So the Stirling cycle is maybe a bit unknown cycle for heat pump applications. So I'm going to give a sort of very brief history of the Stirling engine, then some basic thermodynamics so that you get a feeling about how it actually works. And then I'm going to give some real-world example of the heat pump and some tests that we did on one of our heat pumps. And then I'll wrap it up with some environmental impact, like how is the heat pump comparing to oil boilers or natural gas boilers. So first, some things that I would like you to remember for the Stirling cycle as a heat pump. It's potentially high efficiency. So the process theoretically has the same efficiency as the Carnot cycle. So you can potentially make a good high efficiency heat pump. You can of course ruin it, so it's not a given that it's going to be high efficiency, but it's possible. It's also possible to do high temperature lifts and also high temperatures, because there's no evaporation or condensation of the working medium. So it's staying a gas throughout the process. So it's very adaptive to different processes or different temperatures. The only limits that we have now, well, only limits, is for the temperatures are the materials. So different kinds of seals. So if we go above 200 degrees, then it can be a bit tricky to find a material that would withstand this type of heat. Otherwise, the process is perfectly capable of higher temperatures. So as I said, it's going to be a very brief history of the Stirling cycle, but it was invented by this gentleman on the left, Robert Stirling from Scotland. He got his hot air engine patent in 1816. It was developed as a safe alternative to the steam engine, which has a tendency to blow up at the time. And there were some developments maybe sort of 20 years after the patent, but then nothing much really happened on the Stirling front due to the material constraints until the Dutch company Philips in the beginning of 1930s, 1940s, started to develop an alternative for batteries for the radios. Philips was also the company that gave Stirling engine the name Stirling engine. They started to develop, they made quite a lot of interesting engines. Then in the 1960s, the technology on batteries and also electronics had gone so far that they actually didn't need it. So the Stirling engine was sold off. And now the modern Stirling engine was mainly developed by the American Space Agency for space, and also General Motors in the early 1970s experimented with the Stirling engine. They also made a hybrid car powered by a Stirling engine. And then the Stirling engine that you see on the right there is from a Swedish submarine So it's the air independent propulsion unit made by Kockums. It's now Saab, I think. So that was a very brief history of the Stirling engine. There are different ways of implementing the Stirling engines. So 3 groups that I found sort of useful. It's first the kinematic, so it's driven by a crank. So the one, let's see if I can find the pointer. Nope, sorry, I'll go back again. Can you see my pointer, by the way?
Yeah, slightly. Yeah, we can see.
Slightly.
Okay.
Okay.
Yeah.
Yeah. Okay. Fine.
It works.
Yeah. So this is an alpha. So it's driven by a crank with 2 cylinders and then connected with heat exchangers. So there's fully open, and then there's the heat source, and the heat sink is flowing through the heat exchangers. I'll go a bit more in detail on this design later. Then there is another design which is really interesting. It's a 3 piston one, which you can kind of make hermetically completely sealed, where there's no crank, but you have springs instead. So it's sort of driven by springs. So the piston is connected to springs and the damper. Then there's the thermoacoustic heat pumps. This is kind of the classic design, where you have like a loudspeaker, and then you have standing waves. So you have your resonant boxes for getting the waves, sort of traveling waves, transferring the heat through the heat exchangers. So if you go to the thermodynamics of the Stirling engine, now I'm looking in respect as a heat pump and not as an engine. So it consists of 4 processes. It's constant volume cooling is the first, and then isothermal, so constant temperature expansion, constant volume heating, and then finally constant temperature compression. So if we follow on the PV diagram, so the pressure volume diagram, if we go from A to D, we have the cooling at a constant volume. And then we have the isothermal expansion from B to C. So in order to keep the temperature constant while you're expanding, you will need to add heat. So for an ideal gas, this will be the amount of heat that you will add. Then you have the constant volume heating, so you get up to the high temperature. And then you have the constant temperature compression, where the gas is compressed at the constant temperature. And again, if you want to keep a constant temperature during compression, you also need to remove heat. Then simple energy balance, you can calculate the work. So you have the work and the heat flows, and then you can calculate the COP for an ideal cycle, and you'd find out that it's the same as for a Carnot heat pump. I kind of glossed over the energy, the heat flow here from the cooling and the heating at the constant volume. This is a critical part of the Stirling engine because this is where its internal heat flow. So here you have heat flowing through the regenerator or to the storage, where it's kept. And then when you need to heat the gas again, you take the heat from the heat storage. So this is kind of a key to get the efficiency of the heat pump. So if we go a bit more sort of technical into how you want to implement this kind of cycle in a heat pump, there was, as I mentioned, there is this kinematically driven configurations for a Stirling engine. There are basically 3 different versions. There's an alpha, beta, and gamma, which varies slightly in how they are configured. The alpha and the gamma has 2 cylinders. The beta have only 1 cylinder, but it has 2 pistons inside the cylinder, while the gamma has 2 cylinders that perform different tasks. The alpha has 2 cylinders that's doing the same thing. So if we look at the alpha, you have the piston, you have the cylinder on the cold side, you have the hot cylinder and the hot side piston, and you have the heat exchangers. So here is the hot side heat exchanger and the cold side heat exchanger, and then you have the regenerator or the heat storage in the middle. And there's no valves or any sort of other separation in this volume, so there's the gas can flow freely from one side to the other. So if we look at this piston when it's moving up and down, you can see that this volume will change. So here we try this. So during one revolution of the crank, you can see how the volume will change up and down on the cold side. Then similarly on the hot side, so this is the hot cylinder when the piston is moving up and down. And what is critical is that the pistons are not moving up and down in sync, so they are out of phase. So here is a 90 degrees out of phase. When you add these 2 volumes together, we add up to the total volume. So that would be like the total volume and the variations for the gas here. And you can see that we have one part where we have an expansion where the volume increases. And then we have the compression where the volume is decreasing. And the key here is to look at during the expansion phase, you can see that the volume on the cold cylinder is larger than the volume on the hot cylinder. So most of the or more of the gas is in the cold side. Similarly, during the compression, then most of the gas is in the hot side. So you expand the cold gas and you compress the hot gas. So that's the way that you get the gas even colder, and it can accept heat from the cold source. Here you have the compression where you're compressing the hot to make it even hotter, and then it can release heat to the hot sink. With some really simple thermodynamics calculations, you can end up for an ideal gas. You can find a simple equation for calculating the pressure as a function of the crank angle. Not going to go more into detail of this, but what you end up with if you're using this equation is a PV diagram that looks more like the real process. Then just to remind you what the ideal process looks like, it's down here on the left. And we can start tracing out a few points during this graph, on this graph. So you can see we have the A, B, C, D points on the PV diagram, and also here on the crank angle and volume diagram. So if you see at the A and C, so these are when the piston is moving the fastest here. During the volume, like the cold side, the A is where you get heat from the cold side, and C is where you extract, where you exhaust the heat to the hot sink. And then you can see the A and D. Oh, sorry, the B and D are in the regions where there's almost equal volume between the hot and the cold. So this is where the process is flowing through the regenerator without compressing or expanding the gas. So when it's flowing from the cold side, heat it up so that gas is quite hot when it comes to the hot side. And the other way, when it's moving this way, it's depositing heat in the regenerator, so it's quite cold when it's already is in the cold side. So this is deceptively simply how you would make a heat pump with the Stirling engine. So for a real case application. This is from one of our installation sites. It's in Sweden. It's the research facility of AstraZeneca outside of Gothenburg. So there are 3 of our early version heat pumps, generation heat pumps here, and then there's a later version heat pump at the end. Our heat pump has an output range of 300 to 740, 750 kilowatts. Temperature ranges, the heat source can be from about -5 to 120 degrees, and the sink can be from about 100 to 183 degrees. The COP depends, of course, on the temperatures, and it's about 1.4 to 2.5 depending on the temperatures. Example applications: waste heat recovery, combined heating and cooling, district heating as the consumer, so we can generate district heating, or as a consumer, so we can use district heating as a heat source to generate steam from the district heating. We have one application where we are using district heating to generate temp bar steam. Then we can also generate district heating from a cold source. This application, we are getting waste heat from the cooling compressors at around 40 degrees, and then we are lifting that heat up to about 10 bar. Now they have reduced the steam pressure slightly, so it's about 9 bar steam that we're generating here. So they were kind enough at AstraZeneca to let us do some experiments on one of the heat pumps. It's kind of a one-size-fits-all heat pump. We wanted to see how the single heat pump here performs at the different temperatures. So here I've kind of drawn up the temperature range that is relevant for our heat pump. We managed to test different loads on these 9 temperatures. This number here is the temperature fraction, so the cold side divided by the hot side in Kelvin. I prefer to use the temperature fraction because it makes more sense thermodynamically than to use the temperature difference. What we ended up with is that the coefficient of performance for the heat pump is almost linear with the temperature fraction. I just want to point out here that the test setup, let me go back, this is not optimized for efficiency, so it's more to see how the system behaves. Anyway, so we have a quite linear relationship between the temperature fraction. So if you want to have a rough estimate of a heat pump, calculate the temperature fraction and then use about 50% of the COP. That would be. I will come back to a more realistic COP values that you can get from the heat pump in the next slide. But also you can see that the internal efficiency, which is the efficiency of only the heat pump with the auxiliary pumps, but not any of the pumps needed to transfer the water to the heat pump. Then you have the external efficiency where all the circulation pumps also are included. You can see that this is maybe not so linear, but that's probably more due to the setup of our test than anything else. You can also see that the off design of the heat pump is it's also pretty linear. And you can compare this the load you can see with the colors, so it's also quite on the linear side. So there's no much difference in the COP when it's running on partial loads. So this is more realistic values for the coefficient of performance on the hot side for the different temperatures. And as I said, you can select kind of any temperatures on these two, and you will get the heat pump running. We also have applications that are running on different temperatures on the different times. So we have one case in the Netherlands, Friesland Campina, in Maasdam, where they have a heat source normally at around 85 degrees. But they also, from time to time, when that heat source is not available, they have another heat source around 30 degrees. And then the heat pump just switch between the heat sources, and you don't need to do anything else than to adjust some temperature ranges in the control system. And that application is generating steam at around 150 degrees. I think it's around 3.5 bar. So then I'm going to talk a little bit about the environmental aspects of implementing a heat pump. One thing is the global warming potential, of course, which is so you can reduce the CO2 emissions by going for electricity depending on the electricity mix. I'll come back to that also. Here is a case study we did on the AstraZeneca case. So we're comparing, we did a life cycle assessment comparing the natural gas boiler, the oil boiler, and the heat pump. And you can see from the Swedish condition, the heat pump was the better environmental choice for almost any of the parameters that we looked at. Then, of course, the devil is in the detail. When you go to the European, so we wrote a paper which was published last year, where we looked at the economic and environmental considerations for implementing a heat pump in Europe. And here you can see maybe a little bit more mixed picture. So if we look at the climate change impact, you can see that if when the countries that are below the blue line, then the heat pump has lower environmental impact than the natural gas boiler. If it's below the white line, then the environmental impact is lower than the oil boiler. So here you can see that for most of Europe, it will be more environmental friendly to have or reduce the climate change impact with a heat pump. But it depends very much on the electricity mix. Then for resource usage, it's the same pictures almost as the climate change impact. But then for human health and the ecosystem impact, it's kind of reverse. This is probably due to that these factors are mostly due to the energy source. So in this case, the electricity, and these two are more related to the material that goes into building the heat pump, because it's a more complex mechanism than the natural gas boiler and the oil boiler. So there's more material going into the manufacture of the heat pump. These are also available, both of the papers. So if you're interested, you can have a closer look at more details to be found there. So yeah, that was sort of very brief introduction to a Stirling engine as a steam generating heat pump. Hopefully you found it interesting.